Hello everyone, I am so excited that you have joined us for our lesson today. Today we are going to be investigating number sequences. This falls under the greater mathematics section of sequences and series. Great, so I'm going to ask you a question. Have you ever thought about number patterns that occur in real life? Maybe your mate is always late and you say, well, it's a pattern of theirs to always be late. Today, we are going to look at mathematical ways to explain patterns and also predict further possibilities and outcomes of patterns. Great, so we're going to have a look at the board. Our concept map for today has specific concepts or words that I'm going to define throughout this lesson, and then later on we're going to look at some examples that explain each of these. So let's have a look at our first concepts. The first concept that we are going to be looking at today is the word term. A term refers to each item that makes up a sequence. Now you may ask, but what is a sequence? A sequence is a set of numbers in a specific order that are formed by a mathematical rule. So here we can see the connection to maths. Why? Well, you may be thinking, well, can I see an example of this? Let's have a look at an example where we can see a term and a sequence. So please, will you follow me on the board? If I have the numbers 2, 4, 6, 8, and 10, I could say that this is a sequence because I have a set of numbers in a specific order. So here I've got a set of numbers in a specific order, and if I'm trying to look at a term of the sequence, a term refers to each item that makes up a sequence. So 2, 4, 6, 8, 10 is my sequence, but it's made up of certain parts. So 2 is a term, 4 is a term, 6 is a term, 8 is a term, and 10 is a term. Each of these make up the sequence. The next concept that I'm going to be looking at is something called a common difference. This is the main property of an arithmetic sequence. Let's have a look at the actual definition for common difference. So please look at the board with me. Common difference is a value that is continuously added, so you can even put a little plus in your notes, or it is continuously subtracted between successive terms. So if I think about the example I had on the previous slide, I had 2, 4, 6, 8 going on. I'm sure that everyone will agree with me that between these terms, I have a common difference. So I'm going to ask you to think at home, what is the common difference? Hopefully, you're going to agree with me that I've added 2 between each of these terms. Because I've added 2 between each of the terms of the sequence, my common difference is 2. And again, I'm going to repeat that the property of a linear pattern is the fact that there is a common difference present. Let's have a look at another example. So we are given the pattern 1, 4, 7, 10, 13, 16, 19, 22, 25 going on. everyone, I want you to think at home. Is there a common difference for this pattern? I'm going to give you a couple of seconds. Is there any value that's being added or subtracted between each of these terms? Is it the same value? Okay, I'm hoping that I'm hearing some mumblings of maybe a 3 being thrown around. Let's have a look at the board. Between 1 and 4, I can see that I added 3. Between 4 and 7, I added 3. And look, again, between 7 and 10, I added 3. Between 10 and 13, I added 3. Between 13 and 16, I added 3. And continuously through this pattern, I can see that I'm adding 3 between each of the terms. So, what does this mean for my sequence? We defined common difference as a value that is continuously added or subtracted between terms. In the example behind me, you can see that we continuously added 3. So, what is my common difference? Positive 3. So let us write that down. Our common difference is 3. Because I have a present common difference, it is a linear sequence. And in our next lesson, we are going to be looking at more different types of patterns or ways that we can actually write mathematical rules to describe what we are seeing in a pattern. But I will see you guys after the break. Welcome back, everyone. I hope that everyone saw some cool ads in between. We are going to be going back to our notes on investigating number sequences. Just before we went to an ad break, we defined common difference, and we spoke about a common difference being a number that is continuously added or subtracted between successive terms. We also mentioned that a common difference is the main property of a linear sequence. Now that we've spoken about linear sequences, I'm going to throw a bit of a spanner in the works. We're now going to look at unique sequences. So these are sequences that don't necessarily have a rule that can be applied continuously. These sequences have their own rule. The first one that we're going to look at was designed by a mathematician called Fibonacci. So let's have a look at his example. So Fibonacci came up with the pattern that goes 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. Now, at home, you might be saying, but you just asked me to look for a common difference. And if you're looking at the pattern that's behind me, there's definitely not a common difference. So, what was Fibonacci doing, and what is this pattern? We are now going to look at the board, and we are going to try and see if there's any sort of mathematical relationship that we can discover between these numbers. So, let us have a look. If I'm looking at the first few numbers, so I have 0, 1, 1, 2, and 3. If I was thinking about doing a common difference, there's a common difference of 1 between 0 and 1, a common difference of 0 between 1 and 1, a common difference of 1 between 1 and 2, and a common difference of 1 between 2 and 3. So we can see that there's no common difference between those numbers. So that means we're going to have to get a bit more creative. So I'm going to erase what I've done with common differences. And at home, I want you to think, are there any sorts of relationships between these numbers? Could I ask you to find the next few terms of this pattern? Okay, I'm going to ask you to look at it, and we're going to now see on the board how we can actually figure this out and what Fibonacci was thinking. So let's have another look at the board. If I look between the first three numbers, I'm going to ask us to look at this number specifically. So this is term 3. Remember, we earlier defined that terms are the numbers that make up a sequence. If I look at term 3, it has a value of 1. But if I look at the two terms that come before it, I can see that term 3 is equal to 0 plus 1. So 1 itself is equal to the sum of the two numbers that come before it. Let's see if that same rule applies to the next term. So I've got the number 2, and if I look at the two numbers that come before it, I have 1 plus 1, which is equal to 2. Let's look at the fifth term. So I have the number 3, and 3 is equal to 1 plus 2. Everyone, I'm hoping that you can kind of see the pattern over here. With Fibonacci sequence, the term value is equal to the sum of the two values that came before that. So I'm going to say that again. Each term value is equal to the sum, so I mean adding the two values of the terms that come before it. So this rule is going to help me find the next two terms of the sequence. Let's write our next two terms down. I want to write down the next two terms of the sequence, and I know that each term is equal to summing the two that come before it. So the next term of this sequence will be equal to 21 plus 34. So we can see that the next term will have a value of 55. I am again going to find the next term, and I'm going to find that by adding 34 plus 55. And I'm hoping that everyone will agree with me that the next term value is 89. So that is the Fibonacci sequence. The next example that I'm going to show you is one using words. So the pattern that I've got behind me is just the word smile. So everyone give me a big smile at home because you're happy to be doing that. The word smile goes in a row. So it's smile, 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 going infinitely on. We've just got those 5 letters being repeated. Let's look at the question behind me and what this pattern is actually going to be asking me. So while we are all smiling, let's look at it. As I said, we've got smile, smile, smile going on and on and on. This pattern is asking me, what will the 222nd letter be? So you might be thinking, okay, well, how am I going to know that? If we look at the word smile, we can see that it is a 5-letter word. So this means I'm going to be using my multiples of 5 to help me find out what the 222nd letter would be. So if I look at the number 222, is 222 a multiple of 5? Not quite. But What is a multiple of 5 if I'm looking at a number that's close to 222? Yes, 220 is a multiple of 5. So 220 is a number that is a multiple of 5 that has occurred close to 222. And we can see that with 220 letters in this pattern, we would have had the word smile repeated 44 times. That means that the pattern will begin again with the 221st term and the 222nd term. This means that the 221st letter will be S, which means that the 222nd letter would have to be M. So, for that particular example, M is the 222nd letter in the pattern. Okay, so I hope that everyone's good with me so far. Take a sip of water. We're going to be looking at another example. This example is a hypothetical one. If you and some friends were going to sit down and have a study group. Okay, let's have a look at the next one. I hope you're all still with me. Wonderful. So this example is essentially saying that if you and a group of friends were to sit down at a table that seated 4 of you, there would be 4 of you sitting in the study group. Then if I were to add another table to the study group and add 2 more chairs, I would now have 6 people at my study group. Then what would happen if I added yet another table? If I were to add another table, I would then have 8 people sitting in my study group. So let's look at the next question. So I hope that everyone's happy. We initially had 4 people at one table, then 6 people at 2 tables, then 8 people at 3 tables. We're going to see if there's any type of pattern between the number of people with the number of tables. Let's have a look at the example. So this example is asking me if I were to add another table, how many students would be able to sit down and study. So we've already discussed that at our first table we have 4 people. We have 6 people when we add another table. And then when I add a third table, we then have 8 people seated to study. This question is now asking me if I were to put 4 tables together. So let's draw our 4 tables. We would then have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people seated. So I'm just going to draw a big 10 over here to illustrate that we would have 10 students seated for the study group. Wonderful, guys. So if our tables are going 4, 6, 8, 10, 4 students at 1 table, 6 students at 2 tables, 8 students at 3 tables, and 10 students at 4 tables. Is there a common difference over here? Remember that a common difference is a value that is continuously added or subtracted between terms. I'm going to use my common difference, and then we're going to discuss what the common difference is now, to help me with further calculations. So let's have another look at this example. We have discussed that I've got 4 people, then 6 people, then 8 people, then 10 people. If I'm looking for the common difference, we can see I've got a common difference of positive 2, a common difference of positive 2, and a common difference of positive 2. So I'm going to write up here, we have a common difference of positive 2. Now I'm going to erase this working just so I've got some space to show my working out for everyone. The question that has been asked of us is to determine how many students will be sitting at 10 tables. Now what we're going to do is try and find a mathematical rule to help me instead of me sitting and drawing 10 little squares, which would be a bit of a mission. So let's look at the mathematical rule that could help me determine how many students will be sitting at 10 tables. So at one table, I have 4 students. At 2 tables, I have 6. 3 tables we discussed we have 8. And 4 tables we discussed that we have 10. So I'm going to ask everyone to see if they can see a connection between the tables and the common difference. At one table, we can see that we just had 4 people. But for the second table, we actually added another 2 people. If I look at 3 tables, I'm sure that everyone will agree that we already had 6 people, and I added a further 2. So over here, if I'm trying to express my number of tables in terms of the number of students that will be seated, here I can see that I had 4 people. At 2 tables, I had 4 people plus my 1 common difference. And then we can see that for the next one, I've got 4 people plus 2 common differences. So if we look at the mathematical rule that can help us determine how many people will be seated at a certain number of tables, it's going to be 4 plus the number of tables minus 1 times 2. So for 10 people, we're going to have the number of people at 10 tables will be 4 plus the number of tables, which is 10, minus 1 times 2. So I'm going to have 4 plus 9 times 2, which is going to give me 22 people are seated at 10 tables. Thank you so much for joining us this far. We're going to cut to an ad break, but we'll be back with more examples soon. See you guys just now. Welcome back, everybody. We are going to be continuing our lesson on investigating number sequences. Now, for this portion of the lesson, we are going to be looking at more specific definitions that help us with number sequences. There are quite a few concepts on the concept map behind me, but in this lesson, we are going to break each of them down and use examples that will hopefully help us understand these definitions a bit more. So let us have a look at our first concept. The first concept is term number. Now, what a term number is that it refers to the position of the term in the sequence. So Tn is the nth term of the pattern, where n is the term number. So we're just saying that we are going to pop a little number where the n is, and that's going to tell me the position of the term in the sequence. So if I say t subscript 1, this means that it is the first term of the pattern, as we can see, we've substituted in a 1 where the n is. T3 is the third term of the pattern because I have substituted in a 3 where n is. We can continue using term number. I could say T732, where n is 732. That means it's the 732nd position of that pattern. So whatever's in that n is telling me the term number. Wonderful. Let's look at the next definition. The next definition is term value. This is the actual value of the term. So we will say that we can substitute in a number that is the actual value of the term. So you'll have Tn is a specific number. So let's have a look at the line below. If I say T7 is 334, that means that the value of the 7th term is 334. So, with that example, 7 is my term number because it is the 7th term, but the 7th term is 334. So the term value is 334. Great, let's look at the next one. We are going to look at the next definition, which is the general term or the nth term. What this means is that if we find the relationship, and the relationship we're meaning the mathematical relationship, between the position of a term and its value, we can find a general formula which matches the pattern and find any term in the sequence. So the general formula is essentially expressed as the nth term. If that's sounding like a lot of English, I'm going to try and break it down a bit. All that it means is that the general term describes a mathematical relationship between n, which is my term number, and Tn, which is my term value. And the relationship between these two can help me determine the sequence itself or particular facts about the sequence. I could find later term values, I could find out which terms have that value, but essentially the general term is the mathematical relationship between the term value and the term number. Great. The first example is that if we are given the pattern 1, 3, 5, 7, 9, the nth term for this pattern is said to be Tn is equal to 2n minus 1. So essentially the nth term is a relationship between Tn and n. So just a reminder, Tn is the term value and n is the term number. The question has asked us to check whether the nth term is correct for this pattern. So the pattern is 1, 3, 5, 7, 9. I have the general terms that has been given to me as Tn is equal to 2n minus 1. In order for me to check if it is in fact the general term for this sequence, I'm going to substitute n is equal to 1, 2, 3 going on to see if the term value matches the term number. So let's see if they match. So if I've substituted 1, I'm going to have 2 times 1 minus 1, which gives me 1. Then if I'm looking at term 2, I'm substituting in 2 for n. So I'm going to have 2 times 2 minus 1, which will give me 3. Then if I'm checking the third term, I'm going to have 2 times 3 minus 1, which gives me 5. Okay, then if I'm looking at term 4, I'm substituting in 4 for n, so I'm going to have 2 times 4 minus 1, which gives me 7. So far I can see that 1, 3, 5, and 7 are correct. I'm then going to see, last but not least, if term 5 is correct, I'm going to say 2 times 5 minus 1, which gives me 9. This is good news, because this means that the general term, when substituting in term numbers, which it was n equals 1, 2, 3, 4, and 5, we could see that the general term matched my actual sequence. So that means that general sequence, or that general term, is correct for that pattern. Wonderful, guys. So we're going to take a bit of an ad break right now, but we'll continue with more examples shortly after this. Welcome back, everybody. We are going to continue our investigating number sequences lesson with a few more examples. I've just defined some more of the definitions that we use in number sequences to help us. The main ones that I've been asking you to focus on term number and term value. Term number refers to the actual position of that term. So if I say T6, that means that is the 6th term within the sequence. Tn refers to term value, and that means the actual value of that term. So if I said T6 is equal to 100, the value of the 6th term is 100. Great. So let us look at another example. So will you please turn your eyes to the screen with me? So we are given another sequence that goes 3, 8, 13, 18. We have 3 questions regarding this sequence. The first one is that we are going to determine the next 3 terms of the pattern. Then we are going to write down the formula for the nth term. So we spoke about that as the general term. We're then going to speak about which term in the sequence has a value of 713. So the first question is to determine the next 3 terms of the pattern. Before we do that, let's talk about some strategies. We've spoken about in the past having a common difference. And a common difference is a value that is continuously added or subtracted between successive terms. So with the example behind me and at home, I'm going to ask you to grab a pen. Is there a common difference for this example? Why don't we check? So we have 3, 8, 13, and then 18. We are looking to see if there is a common difference. If I look between 3 and 8, I can actually see that I added 5. Between 8 and 13, I also added 5. Between 13 and 18, I added 5. So everybody at home, I hope that you'll agree with me that the common difference is positive 5, because I have added 5 continuously between the successive terms. So because my common difference is 5, that's going to help me determine the value of the next 2 terms. Let's write them down. So I'm going to have to add 5 and then add 5 again to get to the next two terms. So if I add 5 to 18, I'm going to have 23. Then if I add 5 again, the next term will be 28. Then if I add another 5 from 28, we can see that the next term will have a value of 33. Wonderful. So with our term difference, or our common difference being 5, we can see that the next three terms are 23, 28, and 33. Let's move on to the next question. We now have the same sequence being 3, 8, 13, and 18. I'm just going to write it out for us. We now need to determine the formula for the nth term Tn. Just a reminder, the general term or finding the nth term means that I need a specific mathematical rule that can help me describe the pattern that I'm seeing. So far, I've seen that I have a common difference of 5. I'm going to check whether that common difference of 5 can help me determine the nth term. Let's have a look. So we know that the common difference is 5, and I need to determine the nth term Tn. So I need a mathematical rule that is going to help me. Now, just as a problem-solving strategy, I'm going to look at the number 5, and I'm going to list the multiples of 5. So we've got 5, 10, 15, 20, going on. And we can see that if I were adding the common differences together, those are the numbers that would be present. But all that I have is the multiples of 5 listed. I'm now going to ask you if you see any relationship between the sequence and the multiples of 5. Please keep in mind that this is term 1, term 2, term 3, and term 4. At home, I'm going to ask you, is there any connection between the pattern that's given to you and the multiples of 5? Let's have a closer look to see if we can see a connection. When we look at the first multiple of 5 in relation to 3, we can see that it is essentially 5 minus 2. Again, if I look at the connection between the second multiple of 5 and term 2, we're going to have a subtraction of 2 to get to the term value of 8. If I look at the third value of the actual term with the third multiple of 5, I can see that I subtract 2 to get from 15 to 13. If I look at the fourth multiple of 5 to get to term 4, I can see that I subtract 2. So, ladies and gentlemen, I'm hoping that you can see that there's a relationship. With regards to the multiples of 5, I multiply 5 by the term number, and then I subtract 2. So that is my general or my nth term for the pattern. Let's write it down. So we can say that the general term for the pattern is equal to 5 multiplied by n, which is the term number, minus 2. So we can just check it. Over here with term 3, we had 5 times 3 minus 2, which gives me 13. So this is my nth term. We're now going to use our nth term for the next example. So this question is going to rely on my actual calculated or determined general term in order to answer the question. Let's read the question together. We are going to determine which term in the sequence has a value of 713. Because we are talking about a value, That means that that is going to be my Tn. So I'm going to replace Tn with 713 because that is the actual term value. And I'm going to equate that to 5n minus 2. Luckily, this is something that everybody has seen before. We are going to solve this as a linear equation where we are isolating n. I'm going to take my 2 over to the other side. So I'm going to have 715 is equal to 5n. Then to get n by itself, I'm just going to use my calculator. I'm going to say 715 divided by 5, which means that 143 is equal to n. So it's the 143rd term of the sequence, which is equal to 713. Wonderful. I hope everybody's with me so far. We're now going to have a look at another example. Same principles, just a different situation. So please look at the board with me, and we're going to read the example together. We have Sarah who subscribes to a limited data plan from Vodacell. The limited data plans cost 120 Rand for 1 gigabyte per month, 135 Rand for 2 gigabytes per month, and 150 Rand for 3 gigabytes per month. We're going to assume that this pattern continues, so we can already see that we've got a pattern. A is asking me to find the general formula for the sequence. B is asking me to use the general formula to determine the cost of 30 gigabytes of data. And then we're going to determine how many gigabytes Sarah can buy for 660 Rand. So, all that I've done on the board behind me is written the 3 amounts paid for the 3 different data deals. We are going to see if there's a relationship between each of these numbers so we can actually determine the nth term for the pattern. Let's have a look at the numbers. We have 120, 135, and 150. We can see that we added 15 each time to these numbers. So from 120 to 135, 115 was added. From 135 to 115, 15 was added. So my common difference is 15. So let's have a look. 1 gigabyte was 120 Rand. 2 gigabytes was 120 Rand plus 15. So I could actually say that's 120 plus 1 common difference. So I'm just going to write CD. That's what I mean by common difference, everybody. Then for 3 gigabytes, we're going to have 120 plus 15 plus 15, which is 120 plus 2 common differences. So everybody, we can see that for 1 gigabyte, we had 120 plus no common differences. But each time I added a common difference, I took 1 less than the actual gigabyte number. So for 3 gigabytes, I had 2 common differences. So I can actually write down my rule is that the cost is 120 Rand with the number of gigabytes purchased minus 1 times 15. So to determine the general formula, we are going to use the general formula to calculate the cost of 30 gigabytes of data. So I'm going to substitute in 30 gigabytes of data into the number of gigabytes purchased. So the cost will be equal to 120 plus 30 minus 1 times 15. So it's going to be 120 plus 29 times 15. And I'm going to use my calculator friend again. So let's clear that. We're going to have 120 plus 29 times 15. So Sarah is going to pay 555 Rand for 30 gigabytes of data. And then the last part of this question is to determine how many gigabytes Sarah will be able to get for 660 Rand. So just a reminder, we've calculated how much it would cost for Sarah to get a certain amount of gigabytes. Now we are given the actual amount, and we're going to determine how many gigabytes Sarah will be able to purchase for this amount. Let's go back to the example. So we're going to have 660 Rand substituted in for my cost, which will be equal to 120 plus the number of gigabytes, we don't know how many gigabytes she's purchased, minus 1 times 15. Great, so now I'm going to solve this as a linear equation. I'm going to have 660 is equal to 120. Distributing this 15 that way, I'm going to have plus 15n minus 15. So I'm going to have 660 is equal to 105 plus 15n. Then if I take the 105 over, I'm going to have 555 is equal to 15n. Then what I'm going to do is divide by 15. So let's get my calculator. 555 divided by 15 will give me 37. So that means Sarah would have bought 37 gigabytes of data. Well, I hope those examples made sense. I'm so glad that you joined us today. Thank you, and I hope that the rest of your day goes well.